He reads it, goes to Laplace and says, Monsieur, this is a beautiful piece of work, brilliant, but you make no mention of the architect of the system. He's referring to God. And Laplace replied, sir, I had no need for that hypothesis.
Ooh, that's a mic drop. Ooh, that is tough. Man.
That's a dig on Napoleon and on Newton.
Yeah.
And on Newton.
I have, oh man, look at that. Yeah,
all right. So let's keep going.
Go ahead.
So now, let's say we have not just the planet and one of its moons, but let's say we have a star and another star, double star system.
Right.
Famously portrayed in what film?
Star Wars.
Star Wars.
Yeah.
All right, of course.
Here, Neil deGrasse Tyson is talking about what happens when you build a model of the universe and resist the urge to insert extra agents just to make yourself feel complete. That restraint is not arrogance, it's discipline. It lets the laws of nature show their power. When you stop asking a model to explain everything all at once, you give it room to explain something sharply, predictively, testably, and that's where the real magic happens. Predictions that land on Tuesday at 3:17 p.m. and the eclipse actually shows up on time. Take the simplest gravitational dance. 2 bodies under Newton's law. That problem is solvable, clean, and elegant. Planets trace ellipses, energy and angular momentum are conserved, and you can write the whole story on a chalkboard. Every transit, every eclipse, every return of a comet lines up with math scribbled centuries ago. That's what a good hypothesis buys you. A small set of rules that compresses a lot of phenomena and keeps being right in places you haven't yet looked. Now, add a third body, and the floor gives way. The 3-body problem has no general closed-form solution. Tiny differences in initial conditions blow up over time. This is chaos, discovered not by poets but by mathematicians like Poincaré. Yet even here, order sneaks back in. Certain arrangements lock into resonances, like Jupiter's moons keeping each other in time. There are special balance points in the combined gravities. Lagrange points, 2 of them, L4 and L5, are stable and collect Trojans, while L1, L2, and L3 are unstable, so spacecraft can linger near them only with periodic station keeping. Trojan asteroids surf safely ahead of and behind Jupiter in its orbit. Our most ambitious telescopes live at a gravitational compromise, L2, where the Earth and Sun tug in a way that lets the James Webb Space Telescope cruise in thermal darkness and stare deep into the past. No divine hand parks it there, dynamics does. Double stars, binary systems, are not rare novelties. They're common. About half of Sun-like stars have stellar companions, fewer among low-mass stars and more among massive ones, so partners are frequent even if single stars overall still outnumber multiples. So the question isn't, can 2 suns exist? It's, what kinds of worlds can form and persist around them? We have names for the possibilities. S-type orbits hug one star with the other, acting as a distant perturber. P-type orbits encircle both stars, a circumbinary path. We've found real examples. Kepler 16b, a Saturn-sized world, circles 2 stars in a nearly perfect plane. Every so often it transits, dipping the light from a pair that eclipse each other. The timing of those dips, the eclipse timing variations, is a clock that lets us infer the planet's presence before we ever see it transit. Stability isn't assumed, it's calculated. If a planet orbits too close to the duo, the gravitational tug-of-war ejects it. Move out far enough, and the forces average into a single, predictable pull. So could 2 suns nourish life? That's the cliffhanger in every childhood memory of a desert planet with twin sunsets. Climate models of circumbinary worlds are not simply poetic. 2 stars mean varying illumination, but that doesn't guarantee chaos at the surface. If the orbit is wide and the stars are relatively calm, the planet can experience seasons that, while complex, are still regular enough for ecosystems to adapt. Obliquity, the tilt of the planet's spin, matters. In our solar system, the moon helps stabilize Earth's tilt. In a binary system, the repeated torques can either stir the tilt chaotically or damp it into a steady rhythm. It depends on masses, distances, and orbital eccentricities. We don't guess. We run simulations constrained by data, and we ask what those simulations predict that we can check next. Sometimes that means looking for dust rings shaped by resonances. Sometimes it means counting the statistics of where circumbinary planets are allowed to exist. The answers are not mystical. They're conditional and quantitative. This is where the philosophy of hypotheses matters. A good hypothesis doesn't just fill a gap, it earns its keep by predicting new facts. Dark matter is a good example. It's not a shrug, it's an inference that knits together galaxy rotation curves, gravitational lensing, the large-scale web of galaxies, and the echo of the Big Bang in the microwave background. It gives us tests, colliders, direct detection experiments, astrophysical signatures to try to break it. If it survives, it buys us more accurate maps of the cosmos. If it fails, we know exactly where. That's very different from invoking a catch-all agent that explains anything and predicts nothing. Simple isn't always right. Efficient is the key. Minimal assumptions, maximal predictive reach. And sometimes the right new thing to add is not a new substance, but a new law. When Uranus didn't obey Newton perfectly, one team hypothesized another planet. Neptune was found. When Mercury misbehaved, there was no planet Vulcan. We needed a better theory, general relativity, to replace a piece of the model. That move paid enormous dividends. GPS works, black holes make sense, the universe expands. Notice the rhythm. Start with the simplest model that accounts for what you see. Keep what works, add only what buys you real predictive power. When anomalies appear, be open to two paths, unseen stuff or new rules. Then test the hell out of both. There's humility in this. We learned that, even with perfect laws, long-term forecasts of complex systems can be impossible. So, we changed the question. Instead of predicting every asteroid's path for 1 billion years, we predict the statistics, how many will hit, how often, with what energies. Weather becomes climate, trajectories become distributions. You give up certainty, and you gain reliability. That's not a retreat, it's wisdom. So, when you watch two suns set over a distant world, you don't need an extra hand to keep them in the sky. The equations do that work, and they do it beautifully. Holding back on unnecessary explanations doesn't diminish wonder. It deepens it. Because the universe is not obliged to line up with our intuitions. It rewards the discipline to ask, what's the smallest set of ideas that actually works? Start there. Let evidence pull you forward. And if, one day, a new idea must be added, demand that it change what you can predict tomorrow morning. That's how you turn awe into understanding, and understanding back into a sharper awe. Like if this was interesting, and hit the subscribe for more.